Video will cover the information on capillary exchange in your study guide section 2.5. So if we take a look at how does blood flow through a capillary, these are the only places in the circulatory system that the vessels are not always completely filled with blood. Everywhere else in your body, the vessels will always be filled with blood, but capillaries not necessarily. And we talked about that in the other video. Because of the precapillary sphincters, when we shunt blood, we close them and we shunt blood to other areas that need the blood at the moment. So you can see that the blood flow is very slow and intermittent through the capillaries. But we need that because the blood needs to be able to exchange things with the surrounding tissues, and it's going to do that by diffusion. So the material, once it's out into the interstitial fluid, is going to go into the cells by diffusion. Material will leave the cells and go out into the interstitial fluid, and then it'll pass across the membrane and across the cell wall or the capillary wall, and then back into the blood. But we need to be able to get fluid. We need to get the blood plasma out of the capillary so that it can diffuse then into the cells. And so blood plasma is going to leave the blood vessel and become interstitial fluid, and then become intracellular fluid, or become lymph, or return back to circulation. So we need to take a look at what kind of forces are going on to allow the exchange of nutrients and fluids and waste products within the capillaries and the tissues that they supply. So we've got a couple of forces that you need to know. The first force is called hydrostatic pressure, and this is the force exerted, like it says, by a fluid pressing against the wall of the vessel or the tube through which it flows. Hydrostatic pressure is not restricted just to our blood vessels. Any tube has hydrostatic pressure in it. But we can say that it's also the same as capillary blood pressure, because that's really what blood pressure is. It's just the force that is exerted on the walls of the vessel. And because of this force, it tends to push fluid through the capillary walls. Hydrostatic pressure is higher at the arterial end of a capillary bed than it is at the venous end of the capillary bed. This hydrostatic pressure or blood pressure is opposed by the hydrostatic pressure of the interstitial fluid, which would be outside of the capillaries, pushing fluid back in. However, because of the lymphatic system that we have within our tissue beds, there really is very little hydrostatic pressure of the interstitial fluid that would push against the capillary walls and resist the flow of blood due to hydrostatic pressure of the capillary, or the flow of plasma out of the capillary from hydrostatic pressure of the capillary. The only time that this hydrostatic pressure of the interstitial fluid is really significant is during edema. And edema can be a huge problem depending on how swollen you are and how much fluid is retained within your tissues, that it can greatly reduce the amount of exchange that can take place and greatly interfere with the healing process, because nutrients and waste products are not being exchanged back and forth, and that tissue fluid can stagnate and just make things miserable. So while edema in an acute situation, as we'll talk about when we get into immunity and the inflammatory response, can be helpful, edema at the same time can also be very detrimental. So net hydrostatic pressure then would be the difference between the hydrostatic pressure of the capillary and the hydrostatic pressure of the interstitial fluid. The second pressure that is important is colloid osmotic pressure. And what colloid osmotic pressure does is moves water back into the capillaries. There's no way for us to push water. We can't pump water. There are no water pumps that act like sodium potassium pumps. We do have water channels. They're called aquaporins. But those only work with osmosis. They only go from areas of high water to low water, but we can't ever make water go back the other way. And so we need to have a means by which water wants to move from where it is. And osmotic pressure is the driving force for that. So as hydrostatic pressure pushes the fluid out into the into the interstitial fluid, the surrounding tissue cells, then osmotic pressure will draw the water back in. And how do we do that is by creating a osmotic gradient where we have large non-diffusible molecules, such as the plasma proteins, in particular albumin. Albumin is a plasma protein made by the liver whose chief function is to create colloid osmotic pressure. So albumin is too large to leave the capillary, and so it will always remain within the bloodstream. So as water is leaving on the arterial end of a capillary bed, the concentration of the albumin molecules as we go down to the venule end of the capillary bed is going to increase because water has left, and so there's going to be a greater concentration of albumin at the distal end of the capillary bed. And so what that does is create this osmotic gradient that's going to draw the water from the interstitial fluid back into the capillary bed. So it says these molecules draw water toward them whenever water concentration in their vicinity is relatively lower than on the opposite side of the capillary membrane, like in the tissues. So osmotic pressure of the capillary will pull water back into the capillary blood. And it's always, osmotic pressure is always drawing water toward a more concentrated side of a semi-permeable membrane. So we can see in this picture here is what's hydrostatic we have the hydrostatic pressure that pushes fluid out of the capillary. Typically, capillary pressure hydrostatic pressure is about 35 millimeters of mercury. And then the osmotic pressure is going to pull the fluid back in with a force of 26. The hydrostatic pressure of the interstitial fluid, like I said, is negligible. So it would be pushing it back in, but it doesn't have any force because it all flows away with the lymphatics. And then the osmotic pressure of the interstitial fluid, because of a concentration out here, very, very slight, very, very slight. We should never see plasma proteins out in the interstitial fluid, because if we do, then this number will be higher, and then the osmotic pressure of the interstitial fluid, and so not as much water will return back to circulation. So when we want to find out where is the fluid going, we always want to do our net filtration pressure equation. So here is the equation for net filtration pressure. So we take the hydrostatic pressure of the capillary and the osmotic pressure of the interstitial fluid. Notice the arrows are both moving out, and we subtract from them the sum of the hydrostatic pressure pushing back in and the osmotic pressure of the capillary pulling back in. So if we look at this is going to be 35 plus 1 minus 26. So our net filtration pressure is 10, and it's in the positive. It's a positive number, which means that fluid is going to leave the capillary bed. So it says, as a result, fluid moves from the capillary into the interstitial space. Well, then what's going to happen down at the venule end after fluid has left the arterial end? So we have net absorption is going to happen at the venous end. So because the pressure has dropped, we have resistance encountered along the capillaries, and we don't have as much water as we had before. Our hydrostatic pressure drops to about 17. Our osmotic pressure does not change, and the reason why it doesn't change is because the albumin concentration hasn't changed. So as long as we didn't all of a sudden infuse more albumin down at the venule end, we're going to have the same osmotic pressure. Hydrostatic pressure of the interstitial fluid is still nothing, and the osmotic pressure of the interstitial fluid is still 1. But if we put these numbers into our net filtration pressure equation, you can see 17 plus 1 is 18 minus 26 is now negative 8. And that is an inward pressure. So it says, notice that the net filtration pressure at the venous end is a negative number. This means that absorption, not filtration, is occurring. So fluid moves from the interstitial space back into the capillary. And if we go back here and we see, okay, this is a 10 out and a 2 back, or an 8 back in, but there's a difference of 2. So how do we account for that difference of 2? Well, that means more fluid stays out into the tissues than comes back, and fortunately we have the lymphatic system to return that back to circulation. So we'll talk more about that when we get into the lymphatics and the immune system. Okay, so I think that's everything in capillary exchange. Answers all the questions. And then if we go to the back of the study guide, what happens to these forces of capillary exchange when you are dehydrated? Hydrostatic pressure goes down, or if you have a blood pressure increase, then it goes up. What happens to these forces when you have swelling or edema? So two things will happen if you have swelling or edema. First, if your hydrostatic pressure level is too high, you can get edema. So people with chronic hypertension or right side failure in the heart are going to end up with edema out in the tissues. Or if you have left side failure in the heart, then you have pulmonary edema. But either way, if this pressure is too high, then you will get swelling out into your tissue beds. Or the other way that you will get swelling back in the tissue beds is if your osmotic pressure is not high enough. And your osmotic pressure wouldn't be high enough if you weren't producing albumin. And you're not going to produce albumin if you have a liver disease. So if you have hepatitis or cirrhosis of the liver or liver cancer, those individuals tend to be swollen. It's a very common characteristic, is edema out in the tissues, because there isn't enough osmotic pressure to bring the fluid back. So there's that. Now, support hose or support stockings or compression socks, wrapping the injury to prevent further swelling or edema is going to help increase the pressure within outside of the capillary to want to force the fluid back in. So we're increasing this hydrostatic pressure out here. Damage. Okay, so anytime that you have damage to the cells in an area through a bruise or a burn or an injury that releases proteins or solutes from the cells into the interstitial space, again, if I have more protein out here or I increase the concentration of the solution out here, that's going to increase this number, this osmotic pressure right here, so more water will be drawn out, and again, we'll get more swelling. So that's why when we have tissue damage, not only is it because of the inflammation that's going on, increased vascular permeability and vasodilation, but also because we increase through the tissue damage the amount of proteins and other substances inside of the interstitial fluid, and that draws the water out as well. And then I mentioned chronic hypertension will also result in this, because your hydrostatic pressure is just going to be higher than what your body is used to. So I believe that's it. This just shows where things are going. So you can take a look at net filtration pressure here, and then this is another way of taking a look at hydrostatic pressure and osmotic pressure. And so those are in the PowerPoints that I gave you, so you can take a look at those slides. And then here's just how it works. Okay, so we have more going out due to higher hydrostatic pressure than we have coming back in. So every minute, about 1.5 milliliters of fluid is left out in the tissue beds, and so the lymphatic system has to return that back to circulation, or within a very short period of time, all of your fluid would remain out in your tissues and not make it back to circulation. Okay, so that's all for now, and then we will go into blood pressure regulation and shock in the next video.